2 more teams to go. Team 18 right now. Team 18, are you guys ready?
Yes, sir.
Go ahead.
Hello, everyone. We are Group 18. My name is Elsa. I have Jonathan, Andrew, Lloyd, and Cindy. Today we're going to be presenting our final Sinino design project. Getting drinking water in some area in the world can be difficult. It can be harder in area with natural disaster. So we decided to come up with an idea of portable water purification system, who is solar powered, who is compact and portable, and who is easy to set up.
Why did we choose to make a solar-powered water purification system? Because water is a necessity for every single person. We need clean water to go into our bodies. It makes up about 60% of our bodies. Another reason why we chose to do this project is because about 3 out of 10 people around the world do not have access to clean water. And this being portable helps with that accessibility. Another thing is that there's several features that we made to make it more user-friendly. One of those features being that it has a continuous water flow of permeated water, and it also it does not require you to come into direct contact with the water source. Another feature is it doesn't require manual hand pumps like regular water filters do, so it makes it a little bit easier. Who are we primarily trying to target? Primarily, we were trying to target emergency response teams or government foundations such as FEMA, or nonprofit organizations such as the American Red Cross, or volunteer departments like the fire department or the National Guard as well. Where can you use this system? You can use it in any natural disaster occurrences where drinking water is scarce. One of these occurrences recently happened, such as Harvey, and also what happened over there in Puerto Rico. A lot of people had issues with getting access to clean water, so this makes it a little bit easier. Another thing is that you can also use it in fresh water sources and in rural environments.
What you see here is a sample of the primary standards that are put out by the EPA for the allowable contaminant levels of our drinking water. It lists certain things, and for example, like disinfectants or disinfection residue, microorganisms, or radiotides, just for example. This is the secondary standards. For the secondary standards, they're not really enforceable by the EPA. The primary are. The secondary standards are contaminants that would cause discoloration to your teeth, to your skin, and also cause odor or weird taste or colors in water. Our project is not for fresh water. It's not a desalinization system. The person carrying it has to be able to carry 50 pounds, and the system does not have a backup system for power right now. If the batteries are dysfunctional or completely drained and you're not near your solar panel, then you'll just have to pack it up and go home. The lead for the submersible pump is 10 foot long, so as long as you're within that distance from your water source, you can drop that submersible pump either vertical or horizontally into your water source to siphon your water.
Those pictures here tell the amazing story about a group of students who actually get together and built an incredible portable water filtration system. The first picture on the top left was our first brainstorming after selecting and buying all the different components. And at first, we wanted to have the solar panel to cover the rust side, but due to the curvature angle and the size, we dropped the idea. We use a piece of cardboard to simulate our casing, so we can take precise measurement to build that box that you have on the right hand side, made of threaded plywood, and so it can fit on the rust side. The top pictures on top represent our first prototype. As you see, we have the electrical circuit on the bottom for more stability while carrying the device, but we changed this idea and put the electrical on top. Why? I'm glad you asked. for more safety, we put the electrical on top, so we don't have any water drops dropping on the electrical system can occur. Those two on the side, on the bottom, and this is the device on open, with the front panel open, and that one on the middle is the inside view. On your right-hand side, you have that the system with the closed door, and on the left-hand side, you have the system into the rest sack, fitting perfectly.
This is a sample of one of our many drawings, which is the divider, which is made of plywood. We used it to separate the booster pump from the batteries. This is a sample of one of our many specifications, which is the submersible pump.
How does our system work? Our system works with three manufacturers: the hydraulic, the filtration, and the power. So I'm going to do a quick run on how our hydraulic schematic works. So whenever you have your system, you're going to be dropping the submersible pump to a water source, and from there, the water is going to go to the inline strainer. From the inline strainer, it's going to go to the booster pump. From the booster pump, the water is going to the cytometer filter. From the cytometer filter, the water is going to a carbon filter. From the carbon filter, the water is going to run to the RO filter, and from there, the water is going to the iodide resin filter. And from the iodide resin filter, the water is going to the UV filter. Whenever the water gets to the UV filter, you're going to have purification coming out of the system, so you can drink it.
To explain the function of the filtrations parts, the submersible pump has a cap on it with some slits on it that are about 1 millimeter wide. And anything that gets past that will get taken up in the inline strainer. We're looking at pieces of leaves, sticks, and bugs. If you lose the cap, things bigger than that might actually fall into the pump, probably about 5 millimeters in width. Next, after that, you're going to have your carbon filters and your sediment filters. There's 2 of each. The sediment filters are for, of course, sediments. Your mud, your clay, sand, and silt. The carbon filter is going to be filtering out your chlorine, your taste, and your weird odors. For the reverse osmosis filter, there's actually 2 exits for that. One of them will be the permeated water, which will turn into the drinking water, and the other one is the excess water that's not able to push through the membrane of the reverse osmosis filter. The size of the membrane is 0.0001 microns, so anything smaller than that will get past the RO, which would be your viruses and your bacteria, which is where the iodized resin filter comes in. That will take care of the viruses, and the UV filter will take care of any bacteria that's left over. Do the manufacturer recommended scheduling for the replacement of the filters. The RO and the UV filters are recommended every year. The carbon filter and the sediment filters every 6 months, and the iodized resin filter every 2,500 liters. That's assuming that the water you're siphoning is not sludge. If it is, then your filters will get clogged a little bit sooner, and you might have to replace them sooner.
The power system lasts for about 1.5 hours with the batteries fully charged, and the solar panel takes about 2 hours to charge the batteries. The data below shows how the power is distributed around the components. The booster pump, the UV blast, and the submersible pump requires a power of about 100 or 125.4 watts, while the batteries provide a power of about 192 watts. The solar panel provides a power of about 100 watts. The cost analysis shows the comparison between the prototype of 1 unit versus the mass production of 1,000 units. The total cost of a 1 unit for the prototype is about roughly around $65,000, while the cost of a unit for the mass production is about roughly around $12,000 based on the $50 per hour charge.
We've ran 2 types of simulations to show the stress analysis and displacement for the half-inch pressure-treated plywood. For the first simulation, we compensated for the weights on the elongated center divider for the batteries and the booster pump. And on the second simulation, we compensated. We actually wanted to put 100 pounds of load onto the system itself to ensure its structural integrity. Also, we did find the safety factor to be about 15, which is more than safe. Here's a short video. You can see the submersible pump in the first bucket. It goes through the system and into the Dasani water bottle. You can see the permeated water with the red tube. That is going to be the drainage coming out of that. The hydraulic specifications that we discovered out of experimentation we get about 0.5 liters for every 4 minutes and 47 seconds, which is roughly around 20 gallons every 12 hours with sunlight. The filtration specifications found the water analysis that we did for the permeated water is about 25 parts per million, and the water source that we got it from was around 289 parts per million. The power specifications that we've also discovered were about 0.15 milliamps going through the system, which is, and also about 11.5 volts.
To summarize or synthesize our achievements here, we can say that we were able to build a continuous flow of purified water, and all that without have any direct contact with the water source, as opposed to our competitor right now. Those two, Lifesaver, we need to scoop the water or pour the water in it and apply a mechanical force. And while we kind of engineer the system so we can cut down the weight of the well sack capacitance, which is around 75 pounds, and that's the average of what the military or the emergency responder can carry. To put our result in perspective, so we're able to produce 20 gallons of clean water during a 12 hours working day, and that can relieve the thirst of 10 families of 4. So for future work, we thinking about a few improvements. We want to cut down the weight again in replacing the 3D plywood that we're using in a lighter material, such as probably carbon fiber. And we also want to have the system more compact. So right now you see that we use some hole strap, and we want to replace those from a snap bracket that will reduce the space between the filters and put the system more compact. We also want to integrate the manual pump and backup batteries in case of running out of batteries and you don't have access to a certain power. And also we also want to add digital sensors and an LCD screen and all that controlled by Arduino, so we can gather more data and it's more user friendly. We definitely want to lower the cost, and that's conclude our presentation. Thank you very much for your patience and for listening, and we're here if you have any questions, comments.
Any questions?
What's your expected maintenance cost per year?
The expected maintenance cost per year will vary depending on the usage. Also, it would vary depending on exactly what you're filtering out. Some water is more sluggish than others, so it would require you to change the filters out more often throughout the year. But the range would probably be anywhere between $400 to $600 per year.
Yeah.
What was so you did a test on your safety factor test, but did you do any testing for bacteria or pH?
Yes.
Yes, we did.
Yes, so the pH after experimentation was around 7.2, and the bacteria, we didn't have any bacteria because when especially the UV and the ionized filter take all that out.
So you didn't test for any bacteria?
I mean, the testing device we used didn't mention any of that, so we just assumed that we didn't have it.
None of us died except
I mean, not really, because the actually device we're using actually set all those parameters for us.
But if the water that you're taking, you talk about sluggish water from different types of water, some microbes can be much smaller, and you can end up sucking up something and then poisoning somebody.
Yes, sir, absolutely.
That's a major consideration.
Yes, sir. I actually looked into that. Giardia is one of the few parasites that can actually pass through the reverse osmosis, which is much smaller than 0.0001 microns. So, but that's.
3.1 is much smaller.
But filtering that out, I did issue, the problem was solved with the iodized resin filter. The water analysis that we would have liked to have done was a little costly for us. It's between $200 to $300. So we.
Just add to the cost.
Yes. But yes, we would love to do that
Personal
analysis.
Yes.
What would you suggest as a material for the cabinet if you were to iterate and refine the design?
Well,
Carbon fiber would probably be better, not the same thickness because it would actually be heavier. But carbon fiber would do fine for the cabinet, and the shape of it would also be different to take up some of the extra space that's in there that's unused.
What about packing the solar array? How do you think you could make that a little more efficient for transportation?
We were looking into having a collapsible one where you can just fold
Okay, we can actually fold it.
and carry it much like a briefcase. But we wanted to have something more integrated with our housing, the rucksack. And whenever we wrapped it around, it was just really uncomfortable is the word I guess you could say, because it's just really, really bulky. But yes, we would like to have something a little bit more like collapsible, and you can either detach or attach.
Actually, we were also thinking about having the solar cell implemented on the rest side, so we can just wire them, and they will be easier to carry out.
Yes.
What about market comparison of the products that are out there, the costs and the types?
Well, if you see that one here is called Lifesaver. They sell it in the retail for about 200 or let's say 185. This one here is for a family of 4 and is around 400, right? And that's like we mentioned earlier. We need to be in direct contact with the water source. So you need to either pour the water in it or scoop it or anything. Compared to our system, you just throw the submersible pump over there. You can be at 10 feet away from the source, and you're still going to filter the system properly.
Yeah, but I mean, and unless I missed it, I'm sorry if I did, but are there any other systems of that type that you guys compared it with somewhere in the world?
Actually, we
An electrical system running integrated with the actual filtration, not that we've found thus far, because integrating electrical and water isn't really, it's not.
Not in a small scale like we did here.
In a compact area is but we would like to, another improvement that we really would like to do is just completely seal off that separation from those two systems.
64,000 is a lot of money. So
Yes, sir.
how do you guys pay for this?
We all,
Grants.
we all chipped in.
The kidney.
Or two.
One of the things that we had as one of the final tests for any potable water solutions that we had on Sydney Design is basically we get toilet water, and whatever is coming out, they drink it. If they drink it, so the final grade is pending.
Actually, we were 6 people. The 6th one actually drank the water.
We have to believe in the product, right?
Yeah.
Well, the first person didn't believe in it, and well, he paid the cost. So.
Usually sixes.
Yeah. Group of 6. Any other question?
How many gallons of water can you get before you have to replace the filter? So I know it varies based on what the source is, but do you have an idea of how many gallons you get?
For the on one of the slides.
Is this like you had 6 months in a year, but you didn't have the flow?
There was one filter.
Yeah, that's gonna be the iodized resin filter, I believe. But I believe that the sediment filter and the carbon filters both would be, if I'm not mistaken, it was several thousand gallons. I want to say
I think it was 2,000.
it was around 2,000 or 3,000 gallons, I believe. And
Someone
for
has to take one and put another column. Yeah, no,
yes, sir. The reverse osmosis is the one you want to be really careful with because that's obviously the most expensive one. That membrane is really, really, really expensive.
How do you know when you need to replace the filters? Is there something?
We wanted to integrate we get to do that, but we would like to integrate a sensor that actually measures all of those the water coming out, so we do know different purification levels at the very end, and if it starts to fluctuate, we'd have to start doing maintenance on everything. But we would like to have the sensors.
Or when the water starts to smell bad.
Or whenever the water starts to smell bad.
Flow meter, like.
Flow meter.
Right.
Just a flow meter, program it based on whatever your filter capacity is.
Right. My main thing on this too was adding like shut-off valves from on the inlets and the outlets, so you keep the pressure on everything on the inside, so you don't have to release anything, and you can just throw the submersible pump in there and start running the system.
Any other question? Did you guys try with any local source?
Yes.
We did actually get some water from Clear Creek in Friendswood, so that's where this water came from, and it's kind of yellowish. It's got some stuff floating around in it. That was one of our samples that we had tested it on before, and
Actually, our last sample was taken on the fountain here in front of HCC. So
The water fountain.
Thank you, Tim.